All right, folks, let's go ahead and let's pick up where we left off with yesterday. I hope that everyone's doing well. Um, Nothing new to report to you folks, and so I want to go ahead and get right into where we left off with yesterday, kind of review with you real quickly what we did, and then move forward with the material. Okay. All right, so we talked about displacement. We talked about the what this concept of displacement is. Now we can use that to describe how an object is moving. Okay, so displacement then is basically the change in position, for an object, and the direction in which that change in position occurs. And so displacement is a vector quantity that we can use to describe the motion of an object. Okay? And so that displacement then is defined then as the initial position and the final position, and the positions then, how we determine the initial and the final position is by setting up a reference, an arbitrary reference that we can use, where we say then that at some point in space, we will call that the zero, which is the starting point, and at some point, and then at the position of the object initially and finally are going to be based upon its position relative to that start point. So if we use the Cartesian, the coordinate graph here that we have here, we have then in this example here then our origin. So let's go ahead and indicate the origin here. The origin here represents 0 meters. So at this point here, we have 0 meters. And so the object then, the race car driver here starts at a position. So the initial position here starts at a position that is 10 meters from the origin. So we have to designate that position from the origin. Okay. And so with that said then, the object, the race car driver here will move and ends up at a position that is different from where he started out. So he does undergo a displacement, and so he ends up at a position that is 60 meters away from the origin. So that's why we have to specify where we will designate where 0 is going to be. Okay? All right, so with that said then, the displacement then, remember, is always going to be x final minus x initial. Okay, so x final minus x initial. The final position here is going to be 60 meters in the 60 meters minus the initial position, which is 10 meters. And so therefore our answer then is going to be 50 meters total displacement. Okay, so this displacement then, remember, is a vector quantity. And so as a vector quantity, we will have to decide then what direction the object has moved in. Okay, and so that also is arbitrary. Direction then is either positive or negative, left or right, up or down. Okay, and so using the Cartesian scale here, coordinate graph here, then what we have then, and again, we can stick with this or we can use our own, but I think if we stick with convention, it just makes it easier for us to assign direction. If you choose your own, you need to make sure then that you are consistent with your direction, because if you're not, then your calculations will be wrong when you do the work. Okay. All right, so with that said, then we will always say then on the x-axis, positive will be towards the right, negative will be towards the left. If we are dealing with an object moving in a vertical direction, then positive will be up the y-axis, and negative will be down the y-axis. Okay, so that's the convention that we will use to describe the motion. So therefore then, this object started out at a position that is in the positive side of the x-axis. So we have a positive 10 here and a positive 60 here. And so therefore, the direction of motion is in the positive direction. The direction of the displacement is in the positive direction. Now, if you take a look at what happens here in the second example here, the initial position of the race car driver is at a position that is 70 meters away from 0. Okay, so the initial position is 70 meters away from 0. And so therefore then, and then he ends up at a position that is 30 meters away from 0. So again, we have to identify the start point here as 0 meters, and this is where we pick it. And so if we pick the 0 point here, x initial then is going to be 70, x final is going to be 30. And so let's go ahead and solve for the displacement. Okay, and so therefore x final then is going to be at a position that's positive 30 meters away from the origin, and x final is going to x initial then is at a position of 70 meters away from the origin. If we do the math there, then the answer then is going to be a negative 40 meters. From the calculation itself, we see then that the displacement then, the object, the race car driver, is moving 40 meters, okay, and he will undergo displacement that is towards the left, towards the negative side. whereas opposed to the top example here, he was moving towards the right. Here now we know he's moving towards the left because of that negative sign. And again, the negative sign does not indicate a less than 0, does not indicate less than 0. It just simply indicates then that we have the direction. So he's moving in the positive direction in the top example. He's moving in the negative direction in the bottom example. So make sure you keep in mind that positive, negative indicates the direction of motion, and the number here indicates how far he moved in that particular direction, how far the object moved in that particular direction. Okay, all right. So with that said, then let's go ahead and let's move forward with this. And so, all right. So I'm sorry. There are your answers there. Okay. So understand this: the total distance traveled is not quite the same as displacement. Displacement only takes into consideration what we start out with and what we end up with, the positions at the beginning and the position at the end. Total distance then takes into account the pathway, so how the object got from start to finish. So using an example here, let's go ahead then and make sure you keep this in mind that the displacement is only takes into consideration 2 positions, okay? Whereas the total distance takes into account how the object traveled. So let's consider then this example of a ball that is being thrown up, and then you catch the ball again. Okay, so let's take this consideration. So here's the ball, and we'll call this. So we're going to move in the vertical direction now. So we're going to use the positive, the y-axis. Okay? So this is, we'll call then where the ball starts out. We'll call that position 0. Okay, so it starts out at 0 meters because it starts out at the origin here. So it starts out at the origin, and then we toss it up. Okay, we toss it up, and let's say then that it gets to a height of about 3 meters. Okay, so we toss it up to get to the height of 3 meters. Therefore, then y initial here is going to be 0 meters. Okay, and y final here will be 3 meters. Okay, so if we talk about only the upward motion, then the displacement, which is a vector quantity, is going to be then 3 meters minus 0 meters, which is going to be 3 meters, and it's going to be in the positive direction. So if we're only looking at the object, the ball being thrown up, it had undergone a displacement of 3 meters. Okay? Now, let's consider this. Okay? If the ball gets thrown up, and then we're going to follow its pathway all the way back down to where it's going to be catch it. Okay? And so in that case, then let's consider this. Y initial then is going to be 0. It starts out at 0. Okay. However, this time y final will be 0 because it ends up where it started out at. This time we're following a different pathway. We're following the pathway up and then back down again. And so therefore, if we calculate for the displacement in this case, then we start out y final is 0 meters. Y initial is 0 meters, and so the total displacement then is 0 meters. Okay, 0 meters. Now, with that said, though, obviously the ball moved. It covered a certain distance. Displacement describes just the initial and the final initial position. But let's consider this here. The ball then traveled up, and then it traveled back down. On the upward pathway, it traveled a total distance of 3 meters, and on the downward pathway, it traveled a total distance of 3 meters as well. So the total distance traveled, and we will designate this as a non-vector quantity, so no bar on top. The total distance traveled then is the distance traveled up plus the distance traveled down, which is a total of 6 meters. Okay, so the ball did cover 6 meters, covered 3 meters going up and 3 meters coming back down. So this is the total distance, but remember the total distance takes into account the pathway, the total pathway that the object took. The displacement only takes into consideration 2 points, the initial and the final positions. Okay, and so that's going to be the key difference between displacement and total distance traveled. Okay. All right, so let's go ahead then and, okay, so the distance is twice the height, and so make sure you keep that in mind, but the displacement is going to be 0. Okay. All right, so in one-dimensional motion then, you're going to have positive or negative values, okay, so make sure you keep that in mind as you move forward. So hopefully you recognize then that the distance and the displacement is going to be different. Given another example here, let's go ahead and take a look at another example here to kind of get this point clear to you, okay? Let's imagine an object here, object A. Okay, object A, I'm sorry, an object moves from point A to point B. Okay, so this is going to be x initial. So it starts out at this point here. That's your next initial. This is your x final. Okay, all right. So the displacement then here, folks, is going to be, and we talked about this is a vector quantity. It's going to be x final position minus initial position. And if you subtract those two here, you will get a some value that is in the positive direction. Okay. Now, if you take a look at this here and you measure, so let's pretend that you measure this length here. You measure this length here, and then you measure this total distance here. And so if you take a look at that, okay, which is going to take into account the total pathway that's going to be taken here. This distance here, this is the distance that's traveled. Okay, and this is your displacement here. Okay, you can obviously tell then that the displacement is less than the total distance traveled. Okay, now the easiest way to kind of wrap your mind around this here then is that we can think of the displacement as the shortest path between 2 points, which then would be a straight line, the shortest path between 2 points. Okay, which means then that would be a straight line. So the shortest distance between 2 points, remember we learned in geometry, would be a straight line. So you would identify the straight line path between 2 points, and that is your displacement. That is your displacement. Okay. The distance, total distance traveled then, is dependent on the pathway. Okay, so if you can imagine then going hiking up a mountain. The shortest distance between the base of the mountain and the top of the mountain would obviously be a straight line. But if you've ever been hiking up a mountain, you realize that then you have to follow the path that is carved out for you. You can't switch back, you have to follow the path, and that is not always going to be the shortest distance. So that is going to be then, that's how we can think about the difference between distance traveled and the total displacement, okay? All right, so let's go ahead then and let's continue forward here. And let me switch this to the laser pointer here, okay? All right, so the difference will, when we talk about the speed and velocity, that this difference here is gonna come to light, and it's gonna be made apparent as well, okay? All right. With that said, then I want to go ahead. We'll get back to that discussion about distance and displacement a little bit more when we start talking about velocity. But you have to also get used to being able to describe motion using a graph. So in physics, then what we typically will see then is that we will describe the motion in terms of numbers and in terms of units, but there will also be equations that we use to describe physical phenomena. Okay, so when we get to the kinematic equations, you'll see that in just a moment, because we can use those equations to predict what will happen. So we can describe motion in terms of numbers and units, but we want to also be able to predict the motion itself. We want to be able to predict what will happen. And we do that by using equations. Okay? And these equations that we come up with in physics are all based upon graphs that we use. We can graph the data, find the equation that fits the particular graph, and then instead of graphing from now on, we can use that equation to predict what will happen if we change certain variables, certain aspects of the motion. So we have to get used to taking raw data and graphing it. Okay? And so the simplest type of graph that we can come up with right now is what's called the position time graph. And so these graphs here basically plot the motion of an object, its position versus time. So basically what we have then is we plot the, if we plot the distance along the y-axis versus time along the x-axis, what we'll see then is we can use that to predict how the object will move over a certain amount of time and over a certain distance. Okay? All right, so with that said then, keep in mind that when we do this, we're gonna talk about certain aspects of this particular graph. We'll talk about the slope of the line, to make sure you review certain aspects of straight line and how we can use that to derive an equation from that. Okay? All right, so why would we want to use these position time graphs? Because if we have a limited data set, that means that we've collected a certain amount of data and that's it. We can go ahead and plot it on our position time graph, and then we can extrapolate or interpolate. Extrapolate means then to extend the graph beyond what the data point that we have, or interpolate, which means then to predict what will happen within that data set that we've collected. Okay, so we will get that if we can get what's called this line of best fit, which is a trend line that we'll talk about, and hopefully we'll be able to practice graphing as well. Okay. And then on top of that, we can predict then positions at certain times. Okay, we can predict positions at certain times. And so we need to learn how to analyze these position time graphs and then make them as well. Okay, so we'll be able to do both in this chapter. Okay, so let's practice analyzing. So here's an example of a position time graph here. Okay, this position time graph designates it. So here we have time along the x-axis and position along the y-axis. Okay, let's make sure you understand what we have here. We've called, this is the arbitrary, this is where we've designated as the origin. Okay, this is the origin here. Now, positive and negative along this graph here does not mean up or down. Okay, make sure you understand this. This does not mean up or down. This does not mean moving left or right. Okay? Understand, this is an object moving in one dimension, one direction, in one dimension. What we have to do that means the object is moving along a straight line. Okay, so it's not moving up, coming back down, and moving towards the left and right. So this is not two-dimensional motion. You got to make sure you keep that in mind. Okay. All right. So with that said, then we have distance, the position, plotted along the y-axis here versus time. Okay, so let's take a look at what happens here. So this object, it starts out at point A. Okay, what we have here then, if you take a look at this, then at time zero, so at time zero, the object starts out at point A. So the time is equal to 0. Okay, let's go ahead and describe what happens. If time is equal to 0, the object starts out not at 0 meters, but it starts out at a distance that is what, 30 meters. Starts out 30 meters from the origin. All right. So at time equals 0, its position, and we're going to call this on x-axis, its position is at 30, positive 30 meters. Okay, so at time is equal to 0, it started out at a position that's 30 meters away. Okay, so that's what point A represents here. So that is point A. Okay, let's take a look at point B. At point B, then, the time now, if you take a look at this, the time now is 10 seconds. Okay, we've progressed 10 seconds, so T is equal to 10 seconds. Okay, so time here is 10 seconds after we've started. Okay, so 10 seconds after. Okay. And if you notice here, what the object has done then, its position here now is at, all this x is equal to 10, its position now is at a position of what, 50 meters. Okay, from the origin, not 50 meters from where he started out at, not from 50 meters where he started out at, but 50 meters from the origin. So if you can imagine here, do the math, the displacement then is going to be 20 meters. He had moved 20 meters in the positive direction. Okay, so if you take x final here minus x initial, the displacement at this point then is going to be 20 meters. Again, this represents then a 50 meters from the origin. Okay. All right, let's take a look at what happens at point C. Okay. At point C now, time is progressing. Now we are at 20 seconds into the motion. Okay. We're 20 seconds into the motion. Time here is 20 seconds. So 20 seconds later, that's essentially what we're doing here. 20 seconds later, the object now, so at x equals 20, is at a position now that is roughly about what, 38 meters. So what has the object done here? The object then started out at 30 meters, moved 20 meters away, and then turns around, because now at 20 seconds, he is at 38 meters, which is closer to where he started out. He's only about 8 meters away from where he started out at. Okay, so understand what we have here is that the object started out 30 meters, moved 20 meters away, turned around, and then comes back towards where he started out at. Okay, all right, let's take a look at point D, and let's continue on with this. At point D, we are at 30 seconds from when we started. Okay, so time now, so you can imagine that 30 seconds has elapsed. Okay, 30 seconds has elapsed. Okay, and where is the object? Where is the object now. Where is the person now? The person now is at a position that is x is equal to 0. So not that he hasn't moved. Make sure you understand this. What he has done is he's moved back and he's moved towards the origin. Okay? So can you imagine then what has happened here is that the person now has moved beyond where he started out at, and now he is at this position here. So if you were to calculate the displacement, then this is at x equals to 30. Okay, the displacement then is t final minus t initial. He would have moved a negative 30 meters during this whole 30 seconds here, during the 30 seconds. Okay, so let's imagine this. He starts out at 30 meters away from some point that we call the origin. Let's imagine we put a flag right here. Okay, he starts out of position 30 meters away. He moves towards the 50-meter mark. He moves away from the origin further, but then he turns around and then he starts moving back towards the origin. He starts moving back to origin, but now he ends up back at the origin itself. Okay, so this flag that we placed on the ground. Okay, and so with that said, then if you continue on, and hopefully, let me go ahead and write it down here, folks. So at the point E, so at the position E here, okay, we now have 40 seconds has elapsed. Okay, so the time now is 40 seconds from the time we started out at way over here. So we have an elapsed time of 40 seconds. Okay, and at this point, then he is at a position, okay, at time position of equals 40 that is negative, and make sure you keep this in mind, negative 38 meters. Okay, this does not mean that he's moved negative distance. It just means then he continues to move towards, now he is on the other side, and he continues to move away from the origin and continues in the opposite direction. He moves in one direction, then he turns around, he starts to move in the opposite direction, he continues to move in that opposite direction as well, and that's what we have here. And then finally at point F, and I'm running out of time there. At point F, if you notice then, the elapsed time now is 50 seconds. Okay, so the elapsed time is 50 seconds. Now we are almost a minute into the motion, and his position here at 50 seconds is almost, so negative 58 meters away. Again, does not mean that he's moved in less than 0. This means that he continues to move in that direction and puts him at a position that is 58 meters away from the origin. Okay. All right, so let's go ahead and plot, imagine what we have here. So this is our object. Okay, there is our person. Okay, and we're going to plant our flag here. And so let's plot this along the x-axis. So let's imagine this object moving along the x-axis here. So we're going to plot him along the x-axis with 0 right here. There's 0 meters. Okay. And again, like I said, this object is moving in 1 dimension, not 2. Okay, so let's put him on the, let's imagine this is a ground, the floor somewhere. Okay. All right, so this is the time 0. At time 0, he is at a position that is 40 meters away from the origin. So this distance here is 40 meters away from the origin. He's 40 meters away. This is going to be x initial. Okay. Then he moves in that direction, the positive direction, so that he ends up at point B. So this is point A. He moves at point B. At this point, then he at time here, which is equal to 10 seconds. At time is equal to 10. Okay. Sorry, time is equal to 10. His position now is 50 meters away. Okay, so he gets here, and then what does he do? He turns around. So this is position B. He turns around, okay, and then he ends up at a position here, and we'll call this, this was time is 20 seconds at point C. 20 seconds, okay. He ends up at a position here, and let me draw the dash line, sorry, real quick. It's gonna let me. Okay, that is what, 38 meters? I'm sorry, not 40 meters. This is about 30. We started out at 38. Sorry, roughly about 38 meters here. Sorry, 30 meters. Sorry. Okay, and then we end up at a position that is about 38 meters from where he started. Okay, and what we see here at point D, he continues to move in this direction now, in the negative direction. And he ends up here at point D, which is time is equal to 30 seconds. Okay. Ends up at a position here that is at 0. All right, so I'm running out of time here. And so what I would like you to do, is this is my drawing here. I want you to continue this drawing and show me then where this object ends up at 40 seconds and at 50 seconds. So I want you to draw this, and now I want you to finish up this drawing here, okay, on your paper for submission. And you show me where does the object end up, where's the object at point E, and where's the object at point F. Okay, so please make sure you do that drawing. We don't have class tomorrow. Because we have it's a student holiday for you folks, and it's in service for us. So we won't be meeting tomorrow, but remember, from here on out, we will be meeting every Friday. So on Monday, then, I'm going to finish this drawing for you. On Monday, I'll finish this drawing for you, and you have to be able to, folks, connect what we have here, the information given to us on the position time graph, to what the actual motion is here. Okay, so what I'm asking you to do then is to finish this graph here, this picture here, that shows the actual motion of the object. Okay, and we'll continue with this on Monday. Okay, so please make sure you finish up this graph. So I've given you, I've shown you the object's position and the actual motion for point A, B, and C. I want you to show me where, and D, I'm sorry, point A, B, C, and D. I want you to show me where the object is at point E and F here, on the graph. Okay, all right. Very good, folks. So I will, please make sure you finish that drawing, and I will see you on Monday. Have a good weekend.